Hi, I'm Neil deGrasse, and today I'm going to tell you 100 mind-blowing facts about black holes. Subscribe and let's get started. Number one, what is a black hole? A black hole is a tiny region of space where an enormous amount of mass is packed so tightly that its gravity becomes overwhelming. So strong that not even light can escape once you cross the event horizon, the point of no return. Number two, how are black holes formed? Most black holes are born when a very massive star runs out of nuclear fuel and its core collapses under its own gravity. The outer layers may explode as a supernova, while the core is squeezed so tightly that not even light can escape, creating an event horizon. Smaller ones can also form when dense objects like neutron stars merge. And the giant supermassive black holes at galaxy centers likely grew over time by swallowing gas, stars, and other black holes. Number three, can a black hole die? Yes, a black hole can slowly die through a process called Hawking radiation, which causes it to lose energy over time. Stephen Hawking discovered that black holes emit very weak radiation due to quantum effects. This radiation causes them to lose mass little by little over billions of years. They could evaporate completely. The smaller ones would disappear faster in a final burst of energy. Thus, even the giants of the cosmos have an end. Number four, black holes don't suck like cosmic vacuum cleaners. A black hole doesn't actively suck everything around it like a vacuum cleaner. Only matter that gets too close to its event horizon is trapped because there the speed needed to escape exceeds that of light. The idea that it constantly attracts everything is a myth propagated by exaggerated representations. Number five, if you fall into a black hole, you would experience spaghettification. When you fall toward a black hole, gravity pulls harder on the part of you that's closer to it. Your feet are closer than your head, so your feet get pulled more. This difference in pull is called a tidal force. Because of that, you'd be stretched from head to toe and squeezed from side to side. Scientists jokingly call this spaghettification. You'd be stretched out like a long, thin noodle. That's the whole idea. Stronger pull on the near side, weaker pull on the far side, stretch and squeeze. In small black holes, it happens quickly. In giant ones, you might not notice it until you're deeper in. Number six, there are supermassive black holes at the center of almost all galaxies. At the center of almost every large galaxy is a supermassive black hole, millions or billions of times the mass of the sun. These are not just there. Their mass is closely linked to that of the stars around them, suggesting that the formation of the galaxy and the black hole have evolved together. Number seven, time stands still at the event horizon. Imagine a black hole has an invisible magic circle around it, the event horizon. If you drop a toy clock toward that circle, people watching from far away would see the clock tick slower and slower. Like a video in super slow motion, and its light would look redder and fainter, so it seems to freeze right at the edge. But for someone riding with the clock, everything feels normal. Their heart beats. They blink and they cross the magic circle in just a short, regular time. So from far away, it looks like time stops at the edge. But for the person falling, time keeps going like usual. Number eight, 4 ways to spot black holes. Astronomers see black holes by their effects. First, if a nearby star races in a tight loop or wobbles around an invisible heavyweight, that motion gives away a black hole, like stars speeding around our galaxy's center. Second, falling gas makes a hot accretion disk that rubs and crashes, heating up so much it shines in X-rays, a bright beacon even though the hole itself is dark. Third, when 2 black holes merge, they shake space like ripples in a pond. Detectors on Earth hear this tiny chirp of gravitational waves and can tell the masses and distance. Fourth, a black hole's gravity can act like a magnifying glass. Gravitational lensing. If it passes in front of a far star, the star briefly looks brighter, revealing the hidden mass. Number 9. Einstein didn't discover black holes. Einstein made the rules for how gravity bends space and time, but he didn't discover black holes themselves. In 1915, another scientist, Carl Schwarzschild, used Einstein's new math and showed that if you squeeze enough mass into a tiny space, you get a place where not even light can escape. A black hole. He found the Schwarzschild radius, which is like a too small limit. If you crush something inside that size, it must become a black hole. So Einstein wrote the theory, and Schwarzschild was the first to use it to show black holes could really exist. Number 10, what happens when massive stars collapse? When a huge star burns up its fuel, it can't make the pushback pressure from fusion anymore, so gravity takes over. The star's center or core suddenly crushes inward, while the outside can blow off in a giant explosion called a supernova. Some of that stuff can also fall back in. If the leftover core isn't too heavy, It squeezes into a neutron star about the size of a city but heavier than the sun. But if the core is really heavy, roughly 2 to 3 times the sun's mass or more, nothing can stop the collapse, and it becomes a black hole, a place where gravity is so strong that not even light can escape. Number 11. How black holes get their names. Black holes are usually named after where they are in the sky and how they were found. If X-ray telescopes spot one in the Cygnus constellation, it might be called Cygnus X1. X for X-rays. The giant at our galaxy's center is Sagittarius A asterisk because it sits in the Sagittarius constellation, and the star A there looks special. Number 12. What is the accretion disk? A black hole's accretion disk is a fast-spinning pancake of gas, dust, and super-hot plasma swirling around the black hole because of its super-strong gravity. As the material rubs together and crashes inside the disk, it heats up to incredible temperatures and shines, often giving off X-rays. What's it for? The disk is how the black hole eats and grows, and that bright light lets scientists see where a black hole is, measure how big and fast it's spinning, and study powerful outflows called jets. It is like a glowing disk, like a neon sign that tells us it's there and what it's doing. Number 13. A black hole is not black. A black hole is not truly black because it emits both Hawking radiation and radiation from its accretion disk, although the black hole itself is technically invisible. And the colors and images are often added for visual representation. The term black refers to its gravitational pull so strong that nothing, not even light, can escape from within the event horizon. Number 14, primordial black holes could have formed in the Big Bang. Primordial black holes are theoretical objects that could have formed in the first fractions of a second after the Big Bang, when the universe was extremely dense and hot. It is thought that, due to small fluctuations in the density of matter, some regions of space could have collapsed directly into black holes without going through the stellar phase. These primordial black holes could range in size from subatomic particles to much larger masses. Number 15, what's at the center of a black hole? The center of a black hole, known as a singularity, is a region where matter is concentrated at a point of infinite density, and the curvature of space-time becomes infinite. At this point, the laws of physics as we understand them cease to apply. Although general relativity predicts the existence of singularities, it cannot accurately describe what happens in them due to the lack of a quantum theory of gravity. Therefore, the study of singularities remains an active area of research in theoretical physics. Number 16, the first discovered black hole, Cygnus X1. Cygnus X1 was the first famous black hole candidate, found in the 60s as a super bright X-ray spot in the sky. It lives in the Cygnus constellation and is about 10 times the mass of the Sun. We can't see the hole itself, but it has a big blue companion star that loses gas. That gas spirals toward the black hole, heats up to extreme temperatures, and shines in X-rays that satellites can detect. The star's tiny wobble also shows it's orbiting something very heavy but invisible. Perfect clues for a black hole. Number 17, black holes have 3 layers. Think of a black hole like a super deep well with invisible walls. The outer edge is the event horizon. Once you cross this boundary, nothing can get back out. In some kinds of black holes that spin or carry electric charge, there can be a second inner horizon deeper in, where space and time get even stranger. At the very center is the singularity, a tiny spot where our current physics breaks down and gravity would crush anything. Outside the horizon, you can still escape if you're far enough away. Cross the outer horizon and you're on a one-way trip inward toward the center. Number 18. The entropy of a black hole is proportional to the area of its horizon. Think of entropy as a measure of how many ways something can be arranged, or how mixed up it is. For black holes, the surprising part is that their entropy doesn't grow with how much space is inside them, but with the area of their surface, the event horizon. It's like all the info about what fell in gets written on the black hole's outer skin, as if the surface were made of tiny pixels storing data. This idea, pioneered by Bekenstein and Hawking, led scientists to the holographic notion that a 3D thing can be described by a 2D surface. More horizon area, more entropy, and more information the black hole can hold. Number 19, if 2 black holes merge, the resultant is lighter than the sum. When 2 black holes merge, the resulting black hole has less mass than the sum of the original masses. This happens because part of the mass is transformed into energy and released in the form of gravitational waves. For example, in the G-Way 190521 merger, 2 black holes of 66 and 85 solar masses formed one of 142 solar masses, losing about 5% of their mass in energy. This process confirms the equivalence between mass and energy predicted by Einstein. Number 20, there are four types of black holes. Let's start with Schwarzschild black holes. Think of the simplest black hole, a perfectly still round pit in space. It doesn't spin and has no electric charge. Its key feature is the event horizon, the point of no return. Outside that edge, space is calm and symmetric. Cross it and nothing, not even light, can escape. Another is Kerr black holes. This kind of black hole spins like a top and has no electric charge. Because it spins, it pulls nearby space like a whirlpool, making a special zone just outside the edge called the ergosphere. In that zone, everything has to swirl along with the spin, with strong magnetic fields. This spinning can also help shoot out powerful jets of energy and matter from near the black hole's poles. Continue with Reissner-Nordstrom black holes. This one doesn't spin, but it does carry electric charge. The charge changes the shape of the gravity well, and in ideal math, it can create two horizons instead of one. In simple terms, it's like the basic black hole, but with an electric twist that affects how things fall in and how light moves nearby. Finally, Kerr-Newman black holes, the most complete version. It spins and has electric charge. It combines the swirling space of a Kerr black hole with the charged effects of a Reissner-Nordstrom one. Near it, space-time both twists because of spin and is shaped by charge, making paths of particles and light especially complex. Number 21, the most distant known black hole is 13 billion light-years away. Astronomers first found a very far-away black hole in the quasar J0 313 1806, about 13 billion light-years from us. It's a giant, about 1.6 billion times the Sun's mass, and we see it when the universe was a baby, only 670 million years old because its light took so long to reach us. Later, space telescopes spotted an even farther one called EU-Ike Z1, whose light began just 470 million years after the Big Bang, about 13.2 billion light-years away. Number 22, can microscopic black holes exist? Maybe. Some ideas in physics say tiny micro black holes could have formed right after the Big Bang when the universe was super hot and squished. These would be much smaller than any star, so tiny you couldn't see them, and they'd probably disappear fast by leaking energy, called Hawking radiation, like an ice cube melting. We haven't found any yet. Number 23, the ergosphere of a rotating Kerr black hole allows energy to be extracted. Yes, rotating black holes possess a region called the ergosphere, where space-time revolves along with them. In this area, it is possible to extract energy using the Penrose process, proposed by Roger Penrose in 1969. This process involves a particle entering the ergosphere splitting in two. One part falls into the black hole, and another escapes with additional energy. The escaping particle may have more energy than the original, resulting in a net loss of energy for the black hole. Number 24, supermassive black holes regulate star formation. Supermassive black holes at the center of galaxies regulate star formation through their gravitational influence and the energy they release. Their feedback can heat up and eject the gas needed to create new stars, thus limiting star formation in the galaxy. Galaxies with more massive black holes tend to form most of their stars early, while less massive ones allow star formation for longer. Number 25, the first real image of a black hole showed its shadow. The first real image of a black hole was the M87*, which was captured in 2019 by the Event Horizon Telescope. The photograph showed the black hole's shadow surrounded by a bright ring of hot gas, confirming the predictions of general relativity. This achievement made it possible to directly study the structure of black holes and their influence on the surrounding space-time, marking a milestone in astrophysics. Number 26, black holes can launch plasma jets at nearly the speed of light. Around a supermassive black hole, there's a hot spinning disk of gas. Tangled magnetic fields in this disk act like twisted rubber bands. As the black hole spins, those bands channel some of the system's energy and shoot out twin jets from the poles, narrow beams of superhot plasma blasting at almost light speed. The jets don't come from inside the black hole, but from the furious region just outside it, where the disk and magnetic fields do the launching. These jets can stretch far beyond their galaxies, light up space in radio, X-rays, and gamma rays, and are what makes some galaxies look incredibly bright as quasars or blazars. Number 27. The temperature of a black hole is inversely proportional to its mass. A black hole's temperature is inversely proportional to its mass. More massive black holes are cooler. This is due to Hawking radiation, a quantum effect that causes black holes to emit radiation and slowly lose mass. For large black holes, the temperature is extremely low, making their radiation virtually undetectable. In contrast, lower mass black holes could emit more intense radiation and evaporate over time. Number 28, could we create a black hole in a particle accelerator? It is not possible to create a black hole in a particle accelerator like the LICI. Although these accelerators reach very high energies, they are not enough to concentrate the mass needed in a volume so small as to form a black hole. Gravity under these conditions is too weak, so the formation of micro black holes at the LICI is extremely unlikely. Number 29, intermediate mass black holes exist. These weigh about 100 to 1,000,000 suns, too big to be made by one star, but not as huge as the monsters and galaxy centers. They're hard to spot because they don't always eat much, so they stay dim. Scientists hunt for clues, stars racing around a cluster's center, quick X-ray flashes when gas falls in, or gravitational waves when black holes merge. Strong evidence points to this type of black hole in places like dense star clusters. For example, Omega Centauri and small galaxies. These in-between black holes may be the seeds that, by feeding and merging, grow into the supermassive black holes that shape whole galaxies. Number 30. Another type of black hole is the stellar mass one. These are regular-sized black holes made when a very big star runs out of fuel and its core collapses. They usually weigh about a few to a few dozen times the sun. Sometimes up to around 100, but are only tens of kilometers wide, super heavy and super tiny. You can't see them directly, but if they have a nearby star, they can pull in gas that heats up and glows in X-rays. Or they can merge with another black hole and make gravitational waves. They don't vacuum the whole galaxy. Only things that get very close are in danger, so space around them is mostly calm unless you cross the point of no return. Number 31, finally there are supermassive black holes. These are the giant bosses of black holes, sitting at the centers of galaxies. They weigh millions to billions of suns, but their pull is felt mostly near the middle of the galaxy. When gas and stars get too close, they form a hot, whirling accretion disk that can shine so brightly we call it a quasar. And sometimes magnetic fields help launch huge jets of particles. Our own Milky Way has one called Sagittarius A*. Supermassive black holes help shape how galaxies grow by gobbling nearby matter, stirring stars, and sometimes blowing out energy that slows or speeds up star making. Number 32. The nearest black hole is 1560 light-years away. The closest black hole to Earth is Gaia B Ike 1, located 1560 light-years away in the constellation Ophiuchus. It forms a binary system with a star similar to the Sun and has about 9.6 times the mass of the Sun. It was discovered in 2022 by the Gaia mission, which detected the gravitational motion of the companion star. Unlike other black holes, Gaia B Ike 1 does not emit X-rays and can only be observed by its gravitational effects. Number 33, the escape velocity at the event horizon is equal to the speed of light. Imagine trying to blast off from a planet. You need a certain escape speed to get away. At a black hole's event horizon, its invisible edge, that escape speed, is as fast as light, the top speed anything can go. Since nothing can move faster than light, nothing can get out once it's at or inside that edge, not even beams of light. That's why we call it the point of no return. This happens because the black hole's gravity is incredibly strong, just as Einstein's general relativity predicts. Inside the horizon, every possible path you could take points inward. So you're forced toward the center. Number 34, supermassive black holes can shut down. Supermassive black holes can shut down when they stop accreting material, which stops the emission of X-rays and the ejection of jets of particles. Although they still exist, their active galactic core becomes inactive. This state can last from weeks to millions of years, and the black hole can reactivate if it receives material again. Number 35. Does the shape of M87's event horizon match general relativity? Yes. When scientists took a picture of the black hole M87* with the Event Horizon Telescope, they saw a dark center, the shadow, surrounded by a bright ring, exactly what Einstein's general relativity predicts for a spinning black hole. Follow-up images showed the ring staying about the same size and shape even while the brightest part of the ring shifted and the nearby magnetic fields changed. This means the gravity pattern is stable and matches the theory, while the hot gas and fields around it can vary. In short, the ring's size or shape fits general relativity, and the changing glow is the messy, moving stuff around. Number 36, can a black hole have an electric charge? Yes, theoretically, a black hole can have an electric charge. Solutions to the Einstein-Maxwell equations describe electrically charged black holes. such as the Reissner-Nordstrom and Kerr-Newman rotating models. But in real space, black holes sit in clouds of gas and plasma full of positive and negative particles. If a black hole ever gets a charge, opposite charges from around it rush in and cancel it out very fast, like magnets snapping together. The ones we expect to find in the universe are almost perfectly neutral because space quickly balances any extra charge away. Number 37, black holes can bounce off collisions. No, black holes can't bounce off collisions the way particles can. When two black holes collide, they merge to form a larger one, and the energy released manifests itself in the form of gravitational waves. This process is irreversible and does not involve a physical rebound. Number 38, the thermodynamics of black holes. The thermodynamics of black holes indicate that they possess temperature and entropy. Entropy, proposed by Bekenstein, is proportional to the area of the event horizon, while Hawking showed that black holes emit thermal radiation with temperature inversely proportional to their mass. This establishes an analogy with the laws of thermodynamics, allowing black holes to be treated as thermodynamic systems. Number 39, can the sun become a black hole? No, the sun isn't heavy enough. Only very massive stars, dozens of times the sun's mass, can crush themselves into black holes when they die. Our sun will, in about 5 billion years, puff up into a red giant, blow off its outer layers like a glowing shell, and leave behind a small, hot core called a white dwarf about the size of Earth but very dense. This happens because the sun doesn't have enough gravity to keep collapsing. A pressure inside the white dwarf holds it up. So the sun's future is a quiet white dwarf, not a black hole. Number 40, if the sun were to become a black hole, the Earth would continue to orbit the same. If the sun were to become a black hole of the same mass, the Earth would still orbit the same, since gravity depends solely on mass and distance, not on the size of the object. However, the lack of sunlight would cause the freezing of the planet and the extinction of life, as the energy necessary for biological processes disappears. Number 41, stellar mass black holes can be accelerated to thousands of kilometers per second. Some regular-sized black holes made from big stars can zoom through space at thousands of kilometers per second. How do they get so speedy? When the star explodes, the blast can be a little lopsided. Pushing the newborn black hole like a rocket, this shove is called a natal kick. Also, if two black holes merge, the new black hole can get a recoil kick because the escaping ripples in space, gravitational waves, aren't perfectly even. Speeds like 2,000 kilometers per second are so fast you could go around Earth in about 20 seconds. With kicks that strong, a black hole can even be flung out of its star cluster or galaxy, changing where big black holes can grow later on. Number 42, Hawking radiation implies that black holes are not completely black. Hawking radiation proves that black holes are not completely black. Near the event horizon, pairs of particles and antiparticles emerge from the quantum vacuum. One can escape into space while the other falls into the black hole. This causes the black hole to lose mass in a process called evaporation, showing that they also emit energy in the form of thermal radiation. Number 43, can a black hole's magnetic field exceed billions of times that of Earth's? Black holes can have extremely strong magnetic fields much larger than Earth's. Near the event horizon of the M87*, for example, fields of up to 2.6 Tesla, about 400 times stronger than Earth's, have been measured. These fields regulate the fall of matter into the black hole and help form jets of plasma that travel at nearly the speed of light. Number 44, what is the mass of the largest supermassive black hole equivalent to billions of suns? The largest known supermassive black hole is Ton 618 with an estimated mass of 66 billion times that of the Sun. It is located more than 10 billion light-years away in the direction of the constellations Canes Venatici and Coma Berenices. This ultraluminous quasar was first observed in 1957 and has been the subject of studies due to its extraordinary mass and luminosity. Number 45, can you see multiple images of the universe through a black hole? Yes, black holes can generate optical illusions that show multiple images of the universe. This occurs due to the intense curvature of space-time near the event horizon, which acts as a gravitational lens. This distortion can reflect light from different moments in the past, creating a kind of visual history of the universe. In addition, light passing close to a black hole can orbit it temporarily, allowing an observer to see multiple images of the same event from different angles and moments. Number 46. Stars can orbit a supermassive black hole at 5,000 kilometers per second. Near the Milky Way's center, some stars race around our supermassive black hole, Sagittarius A*, like cars, on a tiny, super tight racetrack. One star called S2 zooms at about 5,000 kilometers per second. And another, S 4716, can reach around 8,000 kilometers per second. That's a few percent of light speed. They go fastest when they swing closest to the black hole, where gravity is strongest, like a slingshot. Number 47, black holes could be seeds of new galaxies. Black holes could have been seeds of new galaxies. In the early universe, intermediate mass black holes acted as gravitational cores, attracting gas and matter to form the first galaxies. Over time, they grew by merger or accretion, becoming the supermassive black holes found today in galactic centers. Number 48, could a black hole's event horizon be a deadly firewall? Some scientists wondered if the event horizon, the invisible edge of a black hole, might be like a burning wall of super hot particles that would fry anything crossing it. This idea, called the firewall paradox, tries to solve a puzzle about how information is kept or lost in black holes. But it's not proven, and many experts think there's no real firewall. They believe the edge stays normal, nothing special is felt when crossing, and that information is saved in other clever ways. So, the firewall is a hypothesis to fix a mystery, not a fact, and scientists are still working it out. Number 49. Kerr black holes allow you to travel back in time. In math, a spinning black hole can twist space-time so much that on paper there are loop-like paths that circle back to the past, like walking around a track and ending up at yesterday. But the places where this could happen are deep inside, where space-time is wildly unstable. Tiny bumps grow into huge storms, the forces and radiation would tear anything apart, and the neat loops break down. So while equations hint at time travel routes, nature almost certainly blocks them. In real life, a Kerr black hole won't be a safe time machine. It's more like a dangerous tornado in space you'd never survive. Number 50, matter in an accretion disk orbits at relativistic speeds. Around a black hole, gas and dust form a flat whirling disk, and the closer you get to the center, the faster you must go to stay in orbit, so fast that near the edge, the event horizon, the material can reach about 1/10 the speed of light. At those speeds, particles crash and rub together, making the disk extremely hot and causing it to shine in powerful X-rays. Magnetic fields act like stretched rubber bands, stirring and mixing the gas so it slowly spirals inward. None of this light escapes from inside the black hole. It comes from the super hot region just outside the edge, letting scientists study how matter behaves under the most extreme gravity in the universe. Number 51, black holes can get fat by devouring stars. Black holes can increase their mass by devouring stars, a process called stellar accretion. When a star gets too close, tidal forces tear it apart, forming a bright accretion disk that feeds the black hole. This phenomenon, observed in distant galaxies, helps to understand the evolution of black holes and their impact on the galactic environment. Number 52, is the entropy of a supermassive black hole greater than that of all the stars in its galaxy? Remember that entropy is a measure of the disorder and information it has absorbed and is directly related to the area of its event horizon. The entropy of a supermassive black hole can exceed that of all the stars in its galaxy combined. This is because the entropy of a black hole is proportional to the area of its event horizon. Because of its enormous mass, as in the case of Sagittarius A*, its entropy is extremely high, much greater than the sum of the entropies of all the stars in the Milky Way. Number 53, you can't see a black hole directly. A black hole is black because its gravity is so strong that no light can escape. So our eyes and telescopes can't see the hole itself. But we can spot what it does to nearby stuff. Gas and dust form a hot, swirling disk that shines, often in X-rays. Stars whip around an invisible heavyweight. Sometimes a star gets stretched and torn if it wanders too close. Beams called jets can shoot out from near the poles. And even gravitational waves, tiny ripples in space, can arrive when black holes crash together. Number 54, there are too many black holes to count. Our galaxy, the Milky Way, may have tens of millions, maybe up to 1 billion stellar mass black holes. And there are roughly 100 billion galaxies in the universe, each likely holding millions of small black holes, and usually a supermassive one at the center. Number 55, some black holes could be wormholes. Imagine space as a big sheet, and a wormhole as a secret tunnel that folds the sheet so two faraway places touch. Some scientists wonder if a black hole's center could be the mouth of such a tunnel linking to another spot in our universe, or even another universe. In math, this idea shows up as an Einstein-Rosen bridge. But there's a catch. The tunnel would likely be unstable, snapping shut too fast to travel through, and might need weird exotic matter to hold it open. So far, we have no evidence that real black holes are wormholes. It's a cool possibility we test with telescopes and theories, but for now, it's science fiction more than proven fact. Number 56, black holes can have photon rings. Around a black hole, there's a special racetrack for light called the photon ring. Here, light doesn't fly straight past, but loops around the black hole one or more times before either escaping or falling in. Because the path is so tight and the gravity so strong, these looping light rays bunch up and look like a thin, bright ring around the black hole's dark shadow. We can't see inside the shadow, but this glowing edge helps scientists figure out the black hole's size and spin, how fast it's turning, and test how gravity works in extreme places. Just like the ring seen around the supermassive black hole, M87*. Number 57, the first detection of gravitational waves in a black hole collision. The first detection of gravitational waves, G-Way 150914, occurred on September 14, 2015, using the LIGO detectors. The signal came from the merger of two black holes of 36 and 29 solar masses, forming one of 62 solar masses. The energy released was equivalent to 3 solar masses in gravitational waves. Number 58, intermediate mass black holes could form in dense star clusters. Picture a packed bee swarm of stars where they fly very close together. This is a dense star cluster. In places like that, big stars can crash or merge, making even bigger stars that later collapse, or small black holes can bump into each other and merge again and again. Over time, these pileups can build an intermediate mass black hole, between about 100 and 1,000,000 suns, because these black holes don't always eat much, they're hard to spot, but clues like stars moving extra fast near a cluster's center suggest they're there. A famous example is the cluster Omega Centauri, where the motions of stars hint at a heavy invisible object that could be one of these in-between black holes. Number 59, are singularities always hidden behind event horizons according to cosmic censorship? Think of a singularity as a place where gravity gets so extreme our normal math breaks, like a glitch in the rules. The cosmic censorship idea says nature hides that glitch behind a black hole's event horizon. An invisible wall you can't see past. That way the weird stuff at the center can't mess with the outside universe, so things stay predictable for us. Scientists like this idea, and it fits what we've observed, but it's still a conjecture, not a proven law. Number 60, black holes can form triple systems. Sometimes a black hole doesn't live alone. It can have a close partner, like a star it's eating from, and both can be orbited by a third farther object, making a triple system. If the third one stays far enough away, the whole dance can be stable for a long time. Astronomers think systems like Vi 404 Cygni may work like this. The far visitor can gently tug on the inner pair, changing how fast they spin or how stretched their orbit is, sometimes causing bright flares when extra gas falls in. On much bigger scales, even supermassive black holes in galaxies can have a third giant neighbor. Its tugs can push two black holes closer together until they merge, sending out gravitational waves, tiny ripples in space, that our detectors on Earth can hear. Number 61, matter falling toward a black hole forms a hot river of plasma. When gas and dust get close to a black hole, they don't drop straight in, they make a fast, whirling accretion disk, like a glowing river circling a drain. In this river, the particles crash and rub together, which heats them to millions or even billions of degrees, turning the gas into plasma, a super hot electrically charged soup. That heat makes the disk shine in X-rays and radio waves, so telescopes can spot it even though the black hole itself is invisible. Number 62, can supermassive black holes slow down star formation with their galactic winds? Yes, when a supermassive black hole is eating a lot, its bright, hot disk can push on the surrounding gas and blow powerful winds. These winds can heat the gas or push it out of the galaxy's star-making zones, leaving less raw material to build new stars. This feedback works like a thermostat for the galaxy. Too much gas near the center, the black hole's activity turns up and slows star birth. Later, when things calm down, star formation can pick up again. So black holes don't just swallow stuff, they also shape how galaxies grow by controlling when and where stars can form. Number 63, string theory predicts that singularities could be fuzzballs. Instead of a black hole having a scary infinite point in the middle, string theory suggests it could be a big, tight ball of tiny vibrating strings, like a fuzzy yarn ball made of energy. In this picture, there's no sharp center. The whole fuzzy surface is packed with little bits that can store information about everything that fell in. So the information isn't lost. This helps connect Einstein's gravity, which bends space and time, with quantum rules, which describe the tiny strings. Number 64, black holes can have different topologies. Black holes can have different shapes or topologies depending on the space-time in which they exist. In 4 dimensions, they are spherical, but in theories with more dimensions, they can have shapes such as rings or toroids. These variations help to better understand gravity and the structure of the universe. Number 65, the rotation speed of black holes. Kerr is close to 99% of the maximum possible. Some rotating black holes, called Kerr holes, spin at nearly 99% of the maximum allowable speed. This extreme rotation warps space-time and affects nearby matter. Such velocities influence the formation of accretion disks and the emission of powerful jets of energy. Number 66, neutron stars can collapse into black holes. A neutron star is the crushed core of a dead big star, about the size of a city, but so dense that a teaspoon would weigh billions of tons. There's a hard max weight for neutron stars. If they get heavier than that limit, the inward pull of gravity beats the push-back pressure from the packed neutrons. This can happen if 2 neutron stars merge or if a neutron star gobbles extra matter from a nearby star. Once the limit is passed, the star can't hold itself up, so it collapses all the way into a black hole, a place where not even light can escape. Number 67, the black hole's shadow illusion is actually 2.5 times larger than its horizon. When we see a black hole, we're not seeing the hole. We're seeing a dark shadow against the glowing gas around it. Nearby light gets bent by the black hole's super strong gravity. Some light loops around it and some is pulled in. So the dark circle we observe is inflated by this bending. That makes the shadow about 2.5 times larger than the real edge of the black hole, the event horizon. Think of it like a funhouse mirror for light. The gravity stretches the outline, making the black spot look bigger. Number 68, primordial black holes the size of an atom could have the mass of a mountain. Imagine something as tiny as an atom but weighing as much as a mountain. That's how dense a primordial black hole could be. Scientists think these mini black holes might have formed in the very early universe, when everything was hot and squished. Even though they're super small, their gravity would be extremely strong, so anything that got too close would be pulled in. We haven't found any yet, so there's still an idea we're testing. Number 69, do black holes expand around the universe? It is suggested that supermassive black holes could affect the expansion of the universe through a cosmological coupling. Its internal growth generates energy similar to dark energy, contributing to cosmic acceleration. Observations of elliptical galaxies support this relationship between black holes and the expansion of the universe. Number 70, black holes can remember their accretion history. Black holes can remember their accretion history through changes in their mass, rotation, and charge, which reflect how they have accumulated matter over time. These features directly influence the radiation they emit and the formation of plasma jets, which can extend over enormous distances in the galaxy. In addition, studying the accretion disk and light patterns allows astronomers to reconstruct previous episodes of matter consumption, providing clues about the evolution of the black hole and its interaction with the galactic environment. Number 71, the information paradox questions in black holes. The paradox of information loss in black holes states that, according to general relativity, information that falls into a black hole is lost when it reaches the singularity. However, quantum mechanics holds that information cannot disappear, as this would violate the principle of quantum reversibility. This conflict has been the subject of debate for decades, with proposals such as Hawking's radiation, which suggests that black holes emit radiation and could evaporate, but without transmitting information about what they absorb. Number 72, the Hawking temperature of a solar black hole would be a mere 60 nanokelvin. A black hole the mass of our sun would glow with an unbelievably tiny heat called Hawking radiation, only about 60 nanokelvin, that's 0.0000006 degrees above absolute zero. This happens because tiny quantum jitters near the black hole's edge let a trickle of energy leak out, as if the hole were a super cold ember. But space around us is much warmer. The cosmic microwave background is about 2.7 Kelvin. So this faint glow is drowned out and basically undetectable. In fact, a solar mass black hole would absorb more heat from the universe than it gives off, so it doesn't shrink from Hawking radiation. It just sits there quietly cold. Number 73, younger supermassive black holes grew incredibly fast. The youngest supermassive black holes grew extremely fast, reaching billions of solar masses shortly after the Big Bang. Its rapid growth is due to efficient accretion of matter and mergers with other black holes. Number 74, could a black hole be a doorway to another universe? Some theories suggest that inside a black hole there might not be a destructive singularity, but a tunnel to another region of space-time or a different universe. But these proposals require extreme conditions, such as exotic matter, that stabilizes the path that have not been detected. Until there is real evidence, black holes remain stuff-ending phenomena, not passageways to other worlds. Number 75, black holes can create gravitational lenses. Black holes can function as gravitational lensing because their intense gravity bends space-time around them. This bends and distorts the light of distant stars and galaxies, amplifying their images as seen from Earth. Thanks to this effect, astronomers can study distant objects, measure the mass and distribution of the black hole, and observe characteristic phenomena such as multiple images or Einstein rings that reveal details about the distant universe. Number 76, matter orbiting a black hole undergoes Schwarzschild precession. Matter orbiting a black hole undergoes Schwarzschild precession, an effect of general relativity that causes the orbits to slowly rotate around the black hole. This occurs due to the intense curvature of space-time caused by its mass. It has been observed in stars close to supermassive black holes, such as S2 around Sagittarius A** in the Milky Way. Number 77, black holes are ultra-powerful energy factories. When gas and dust spiral around a black hole in a fast, hot accretion disk, they rub and crash together so much that they heat up to incredible temperatures and shine, from visible light all the way to X-rays. This glowing is energy made from the falling material's motion and gravity. And it can be amazingly efficient. A small part of the stuff's mass is turned into light, much more efficiently than the sun's nuclear fusion. Number 78. In theory, anything can be a black hole if you squeeze it small enough. Gravity depends on how tightly mass is packed. Crush the same mass into a tiny space, and its pull gets super strong. There's a special too small size called the Schwarzschild radius. Shrink an object inside this size, and not even light can escape. For the sun, that size would be about 6 kilometers across, like a city. So if you squashed all the sun into a ball that small, you'd get a black hole. For Earth, it would be about the size of a marble. 9 millimeters. For a person, it would be much smaller than an atom. Number 79. Supermassive black holes could be responsible for the reionization of the universe. After the Big Bang, the universe cooled and filled with a thin fog of hydrogen atoms. Later, powerful light from the first bright objects broke those atoms apart again. This cleanup is called reionization. Many scientists think supermassive black holes helped a lot. When they eat gas, they shine as quasars, blasting intense ultraviolet and X-ray light that can rip electrons off hydrogen, clearing the fog. Giant newborn stars likely help too, so the truth is probably a team effort. Both early stars and feeding black holes lighting up the young universe and making it transparent so light could travel freely. Number 80, a black hole's corona is a region of ultra-relativistic electrons. A black hole's corona is a region composed of ultra-relativistic electrons moving at speeds close to light, located above the accretion disk. These electrons interact with the hot plasma, generating high-energy radiation. Especially in X-rays, the corona influences the total luminosity of the black hole and can participate in the formation of relativistic jets. Number 81, black holes can shoot hypervelocity stars. Near a black hole, two partner stars can wander too close. The black hole's gravity grabs one star and keeps it, but the other gets flung away like a slingshot. This is a hypervelocity star. It can be launched at hundreds or even thousands of kilometers per second, fast enough to escape its galaxy. Number 82, the fastest spinning black hole. Astronomers found a nearby black hole called Maxigi 1820 plus 070 that spins almost as fast as nature allows, like a cosmic top near its speed limit. We can't see the hole itself, but when it had a big flare-up, telescopes watched the hot gas whirling around it and used that light to measure how fast it's turning. Those measurements show its spin is extremely high, very close to the maximum possible for a black hole. Number 83, rotating black holes have two event horizons. A spinning Kerr black hole is like a super-fast whirlpool in space. It has two invisible walls. The outer horizon, which is the point of no return, once you cross it, nothing can escape, and a deeper inner horizon closer to the center where space-time gets even stranger. Number 84, exist the white holes? A white hole is a theoretical idea that's like a black hole in reverse. A black hole pulls things in and nothing can escape. A white hole would only push stuff out and nothing could go in, like a one-way space fountain. In math, you can make a white hole by running a black hole movie backward. And some theories even imagine a white hole connected to a black hole by a wormhole or link it to the Big Bang. But there's a big catch. White holes would be unstable, tiny bumps could make them collapse, and we found no real evidence for them in space. Number 85, black holes can have rings of fire. Black holes can display rings of fire made up of extremely hot gas and plasma that orbit close to the event horizon. The intense gravity bends the light, creating a bright ring. Number 86, black holes make energy more efficiently than normal stars. Stars like our sun shine by fusing atoms, turning less than 1% of their mass into light. But when a black hole is eating, gas in its accretion disk orbits faster and faster the closer it gets to the edge. Rubs together, heats up to incredible temperatures, and gives off huge amounts of energy, much more per kilogram than a star. Typical disks can turn several percent of the falling mass into light, often around 9.3% more efficient than normal stars. And for very fast spinning black holes, even more. Number 87, Kerr black holes allow stable orbits closer to the horizon. A spinning black hole drags space around like a whirlpool, so things that orbit with the spin can safely circle closer to the edge than around a non-spinning black hole. The closest safe racetrack is called the ISCO, the innermost stable circular orbit. For a fast spinner, that racetrack moves inward. If you try to go even closer, your path becomes wobbly and you spiral in. If you orbit against the spin, the safe racetrack sits farther out. This matters because an accretion disk that can get closer gets hotter and brighter, changing the color and strength of the light like more X-rays we see, which helps scientists measure how fast the black hole is spinning. Number 88, EM theory suggests that black holes could be coiled brains. Think of the universe as not just 3D space, but a place with extra tiny dimensions curled up like little tubes. In M theory, the basic building blocks aren't just particles, but stretchy sheets called brains. A black hole, instead of having a scary infinite point inside, could be a brain or stack of brains tightly coiled into those extra dimensions, like a rubber sheet scrunched into a tiny ball. This coiled brain picture spreads the black hole's stuff out so there's no single impossible point, and it gives a way to store information on the surface. Number 89, black holes can silence the universe. When a supermassive black hole at a galaxy's center is eating, the hot, bright disk around it can blow powerful winds and shoot jets that shove or heat the galaxy's gas. The raw stuff needed to make new stars. If that gas gets pushed out or warmed up too much, it can't clump together, so star making slows or even stops. It's like turning off the stove under a soup. No bubbles, no cooking. Galaxies that get blown dry this way can grow quiet and dim over time, with fewer young blue stars, so the black hole hasn't swallowed the whole galaxy, but its energy has quieted the star factory, making the universe a little more silent in that place. Number 90, Einstein's equation has solutions for eternal black holes. Einstein's equation allows solutions that describe eternal black holes, such as Schwarzschild and Kerr's. These ideal models assume a stationary black hole that does not change over time. They are useful for studying the geometry of space-time, near orbital dynamics, and relativistic effects, such as frame drag and light bending. Number 91, black holes can whistle. Black holes do not emit sound in the conventional sense, since outer space is a vacuum that does not transmit sound waves. However, phenomena associated with them, such as pressure waves in the hot gas, can generate vibrations that, when converted to audible frequencies through a process called zoning, produce sounds that resemble a hiss or buzzing. Number 92. Maldaceno's conjecture connects black holes to conformal field theories. Imagine a 3D world with gravity and black holes being like a movie, and all the instructions for that movie are written on a flat 2D ice screen around it. Maldaceno's idea says that for a special kind of universe, everything happening inside, even a black hole, can be perfectly described by a gravity-free theory living on the edge called a conformal field theory. That means hard questions about black holes and quantum gravity can be turned into easier questions about particles and fields on the boundary. Number 93. A quasar is a galaxy that houses a supermassive black hole at its center. A quasar is a supermassive black hole at the center of a galaxy that is actively absorbing matter. The gas and dust that fall towards it form an accretion disk that gets very hot and emits very intense light, making the quasar brighter than the entire galaxy that contains it. In addition, in some cases, it emits jets of particles and very powerful radiation. They are some of the most luminous objects in the universe and allow us to see very distant galaxies. Number 94, black holes can have stars living nearby. A black hole doesn't suck up everything around it like a vacuum. From a safe distance, it pulls on things just like any other heavy object. So stars can orbit a black hole the way Earth orbits the sun, just much faster and closer because the gravity is stronger. In our own galaxy, the supermassive black hole Sagittarius A** has a bunch of fast stars racing around it, whipping by on long stretched paths and then swinging close like a slingshot. Sometimes a star gets too close and gets stretched or loses gas, which can brighten the area. But if it stays at a safe distance, it can loop around the black hole for millions of years without falling in. Number 95, no two black holes are the same. Black holes come in many personalities. Some are small, some are giants, some spin fast, others spin slowly. Their surroundings matter too. A hungry black hole with lots of gas makes a bright, hot disk and sometimes jets. A lonely one stays quiet and dark. How each one was born changes its mass, spin, and even how close things can safely orbit. So just like people have different sizes and habits, every black hole has its own unique story and behavior. Number 96, Hubble Space Telescope and black holes. Hubble is a powerful telescope that orbits above Earth's blurry atmosphere, so it takes extra sharp pictures of galaxies. With those clear views, Hubble has shown that many galaxies have bright, active centers where a supermassive black hole is feeding, and it has helped measure how fast stars and gas move around those centers like clock hands racing, so scientists can weigh the hidden black holes. Hubble has also captured jets and glowing disks of hot gas near black holes and watched how their brightness changes over time. Number 97. Black holes can sleep for millions of years. Black holes can sleep for millions of years if they don't have nearby matter to feed on. In this state, they emit little radiation and generate no observable activity. Although they continue to gravitationally influence their environment, they can be reactivated if they receive new material. Number 98. Perturbation theory predicts that black holes ring like bells. When a black hole gets bumped, say two black holes crash into one, it doesn't just go quiet right away. The new bigger black hole wiggles a little and sends out gravitational waves with special tones, like a bell that's been struck. These tones, called quasi-normal modes, have exact pitches and fade times that depend on the black hole's mass. Bigger is deeper tone, and faster spin changes the notes. Number 99, larger supermassive black holes could swallow the entire solar system. Some black holes are so huge, billions of times the sun's mass, that their no-escape edge would be bigger than our whole solar system. For scale, to cover Neptune's orbit about 30 times the Earth-Sun distance, a black hole needs roughly 1 billion suns of mass. Monsters like the M87* are even larger. If one of those sat where our sun is, every planet, comet, and asteroid would lie inside that boundary and couldn't get out. Don't worry though, the nearest supermassive black hole is very far away, and none of these giants are anywhere near us. Number 100, black hole collisions emit gravitational waves. Imagine two super heavy, invisible marbles dancing on a stretchy trampoline, the space. As they spin closer and closer, they make ripples run across the trampoline. Those ripples are gravitational waves. The closer they get, the faster and bigger the ripples become until, boom, they smoosh into one. Far away, special space ears can feel those ripples as a tiny chirp. Like wee-oo, that chirp carries clues like how big the marbles were, how fast they spun, and how far away the dance happened. And that's all. What black hole fact surprised you the most? Leave it in the comments and subscribe. See you soon, your friend Neil.